Hello, everybody. Welcome back to Markov chains. Okay, we're talking about the MG1 queue. And last time we found the probability that the MG1 queue was empty, but none of the other probabilities because those are really hard to find and they're dependent on the service time distribution. So the MG1 queue, let me start sharing, is a single server queue. And the first M stands for memoryless and means that the inter-arrival times are exponential with rate lambda, just like they were in the MM1. And the G stands for general service times. So we're not going to spend too much more time on the MG1, but we're going to do something today that you can use for any of your other queues. Even your MM1, these might help computations out. This might make computations easier for you in even queues that are not as daunting as the MG1. So what we're going to do is try to come up with the expected mean or average queue length in equilibrium. And so also I promised Zuko, but he's in the middle of shedding like right now, so he's not happy. Okay, so the MG1. So the setup was a Poisson arrival stream with some rate lambda, a server with some rate mu, and then they leave. And so I don't want to take the time to write these again, but the arrival process is Poisson. The service time distribution has some kind of PDF, and it's general. It's not necessarily exponential. So the service time distribution has some PDF, G of X or G of S if you're thinking of service times, or G of T if you're thinking of times. And we're using mu as people normally use mu in queuing theory. It's not a mean, it's a rate. And so if you find the expected service time, you would be looking at the mean for this distribution. So you would have an integral from probably 0 to infinity, although we can have finite service times like uniform service times. So let me leave the limits off. But it would be, I'm going to turn it into S's. S times G of S, ds. And if you compute this, given your particular PDF, you're going to get 1 over mu. So remember, our rate is the mean flipped over. And in queuing theory, we've sort of used up the mu for a rate. So the mean service time is going to be 1 over the rate. And I know that looks very weird because, you know, mu's and means, they're just means. Okay, there's one more thing I'm going to need today regarding this distribution that we didn't talk about last time, and that is the variance of the service time. And so I'm going to call this sigma squared, very classical variance notation. And this is going to be the expected, well, now I need notation. The expected service time squared minus the expected service time all squared. I was really trying to avoid using S's for that because there's so many S's flying around, which is why I kept writing out the words service time. And you can do this first integral by integrating S squared against the service PDF. And we just talked about how to do this one. So the variance is going to come in today. And we haven't talked about variance really at all in this course. And it's not about to ramp up. This is probably the only time we'll be talking about it between now and the end of the course. So Poisson arrival process that is independent of the current state of the system. No one is looking at the number of people in the queue and turning back. Service times are IID from some general distribution with a PDFG. What else do we need to know? One server. I think that's enough. So our goal today, at least for part of today, is going to be to find the expected queue length in equilibrium. Gosh, my word is sliding everywhere. So let's find the mean or expected number of customers in the system. So I always try to make the distinction, but other books won't. And you'll see expected or mean queue length in equilibrium because the whole thing is a queue. And I keep saying this, I'm going to say it just one more time. Right, in Markov, the whole thing is a queue, the system. And in like the English language, the queue is usually the people lined up in a queue. So there's the problem. So I'm going to find the mean or expected. I'm going to write queue length in quotes, but really I mean number of customers in the system in equilibrium. And so the reason I just introduced this variance is because I can get this as a function of that mu and sigma squared. So let's do it. I'm going to let x of t be, actually, let me not denote it as a process. So I can just say equals the number of customers in the system at time t. And then we talked about that kind of reverse pasta property where because the arrivals are Poisson and independent of what's going on in the system, we can look at the chain just prior to an arrival or just after a departure. So the person leaving looks back and sort of notes the state of the system. So the number of customers in the system at time t. And for our purposes today, it's the departure process we want to look at because we talked last time about how this queue is no longer Markovian because if it's moving along and you just come along at some time, you can't tell exactly where you're going next until you know how much of this service time was used up, whereas we don't have that problem with the exponential. So this is why we keep looking at the MG1 just after a departure, because at that point, a new service is starting. And even though it's not exponential, we don't have to worry about lack of memory. We'll have the entire service time ahead of us and not part of it. So just like last time, I let xn be the time embedded post-departure process. And so that means what it has meant. Customer leaving looks behind, and what do they see? Okay, so I want to find L, which there's so much in queuing notation that really conflicts with just standard notation throughout probability. This is going to be the expected queue length in equilibrium. So it's going to be the limit as t goes to infinity of the expected value of the number of customers in the system at time t. And one problem with this is it sort of looks like a random variable being capital, but it's not. It's an expectation, which is this is a sequence of numbers and you can take that limit. And so we want to know this L. We're going to find this L. It's going to be super cool. All right. So let's assume that we are, oh, I would. Yeah, there's so many great things we can confuse this with. Okay, so I'm going to let X, I want to look at the chain at 2 points right after consecutive departures. So like an xn and an xn plus 1, but after the system has reached an equilibrium. And if it's reached an equilibrium, then the n is not important. So I think this is going to go a little nicer. It's going to be a little neater if I just come up with sort of new notation. So I'm going to let x be the number of customers left behind by a departing customer in equilibrium. So it's like an xn, but n, has run off to infinity, or we started stationary. So it's already stationary and we don't really care about the time, which is why I'm losing the n. And then I'm going to let x prime be the number of customers left behind by the next departing customer. We talked about this last time. We defined one of these. We defined xn plus 1 in a piecewise way based on xn. So the next departing. And we said something like the number, I'm going to write it with n's and then I'm going to erase them. So maybe you don't want to copy this if you're taking notes. The number left behind by the n plus first departing customer is going to be the number left behind by the nth departing customer. No, we had the piecewise thing. We said if the number left behind by the nth departing customer was 0, then the number left behind by the n plus first departing customer is just the number of arrivals during the service time of that customer. And we called that YN. I'm about to erase this, so I don't really want to recap what these letters are because we're going to change them over to our new letters. But that was the number of arrivals during the service time of the nth departing. The nth departing customer left no one behind. So the n plus first customer came in, and while they were being served, yn plus 1 people came in. And that's who they're leaving behind. And if xn is greater than or equal to 1, then we have xn minus the customer that left plus the customers that came in during the service time of the nth departing customer. So I'm going to write this without all this notation. This is now my x prime. This is now my x. And I'm going to simply let the number of customers that come in during a typical service period be capital N. Okay, so this is like the yn, or yn plus 1. The point is time doesn't matter, which is why I'm losing the subscripts. So this is, again, like the yn, or yn plus 1. And so I'm going to rewrite this all in one line right now with the new notation. The number of customers left behind by a departing customer is the number of customers left behind by the last customer plus, that's not what I want. I just want to use my x, plus the number of arrivals during the n plus first customer service period, and then minus 1 if and only if there were people in the system when the nth customer left. In other words, I'm about to subtract this 1, but I don't want to subtract it if the previous customer left behind 0 people. So I'm going to write minus an indicator that x is greater than 0. And we haven't used indicators very much in this course, but if we have, I probably didn't write one this way, excuse me, this way. I probably wrote something like a function that will take the value 1 if this variable is in this interval or not. But right now I'm writing like an event indicator. So this is going to be 1 if x takes a value greater than 0 or 0 otherwise. So this is a compact and non-time, ignoring time kind of way to write this mess down. Who's with me? All right, Caden, you speak for everyone because you're the only one I can see right now. So great. I'm glad you're all following. All right, so I want the, again, we want to find L, which is going to be the limit as t goes to infinity of the expected value of the number of customers in the chain at time t. But once we reach stationary mode, this is the same thing as the expected value of x. And it's also the same thing as the expected value of x prime, because we're in that stationary regime where the distribution stays the same between, this is one time point and this is the next time point after we've run it like an infinitely long time. So I'm going to try to use this equation to try to find L, and I'm going to represent it this way because I see some of those in there. So let's try taking the expected value across on this equation. So from here, I'm going to take expectations on both sides. So on the left side here, I get L. That's the definition of L. For this term, I still get L. That's not good for finding L. That my L is going to cancel. For this, I don't know what this is yet. We'll figure it out in a minute. I'm just going to write the expected value of N. And then you've seen a few times, at least a few times in this class, that the expected value of an indicator is the probability of the event being indicated. So I'm going to subtract the probability that X is greater than 0. Because this is a random variable that takes on only 2 values, 1 and 0, nice and discrete. So if you were to write out the expectation, you would end up with 0 plus 1 times this probability. And I know what this probability is because last time we showed this guy that I just circled is 1 minus pi 0. It's 1 minus the probability there's 0 people in the queue in equilibrium. And we saw last time that this is 1 minus lambda over mu. So it is lambda over mu. And so from this and that, it looks like my L's are going to cancel. And look what we found. I mean, we didn't find what we wanted, but this is kind of interesting. Moving things around, I've got the expected value of n is lambda over mu. We found the expected number of arrivals during a typical service time. We've done that in other ways by conditioning on the service time. This was kind of slick, except that it wasn't, because we want to find the expected value of L, and those canceled away. So let's try, instead of looking at taking the expectation through on this, I am going to square this. So I'm going to take x prime and square it, and this is x plus n minus the indicator. By the way, at the end, this will be a formula in a box, and it will be provided on the final exam cheat sheet. Okay, so if I square this right side, I'm going to get x squared, and I'm going to get an n squared, and I'm going to get the indicator squared. I want to rewrite this right-hand side. There's a couple of things I can simplify here. So one is the squared indicator is just equal to the indicator because it's 0 and 1. So if you square it, it's still 0 and 1. So I can kind of ignore that exponent there. Another thing I can do is I can rewrite this guy as 2x, because that indicator is going to zero out if x is 0, otherwise it's going to be 1. But if x is 0, then this is going to be 0 already. So I don't need the indicator to zero that out in the case when x is not greater than 0. Okay, I think that's about it. So let's regroup here. I've got, oh, don't want to do it in that color. Maybe we do. Maybe it's time for something new. Okay, so on the left side, I have this x prime squared, and on the right side, assuming I have all my terms, I have x squared plus n squared minus, oh, that should have been, this one should have been a plus. So plus the indicator squared, but I don't care about the squared because it's 0 and 1. And then minus 2x. And then I'm going to put the other two terms together and write this as plus 2nx minus the indicator. Okay, that's enough of that exciting stimulation of a new color. Go back to white. I want to take the expectation all the way through here. And what is going to happen? I'm going to take the expectation on both sides. And before I do that, let me just look at this term alone so we can simplify it. So the expected value of 2n x minus the indicator, I can pull the 2 out, and x is the number of customers in the system. And this indicator is a function of x, the number of customers in the system. And n is the number arriving during service time. And we had explicitly that that will not depend on what's going on in the system. Like there's no balking. So the people arriving are not looking ahead and making a judgment about whether or not to come into the system based on X. So we do have independence here between the X and the N, which is part of the assumption of the MG1Q. Okay, so I'm going to factor the expectation, because you can do that when you have independence. And then for the second one, I am going to run the expectation through. And I think we already know we just found this. And the expected value of x is L, the thing we're trying to find. So good, even though we canceled out some, we're going to cancel some L's out here. There's a surviving L. And we know the expected value of this because that's the probability that the event being indicated happens. So overall here, I get 2, then lambda over mu, which was the expected value of n, and then I get L, and then the expected value of the indicator is the probability of the event being indicated, and that is 1 minus pi 0, and we already saw that this is lambda over mu. We got an L. We got an L to work with. So when I finish taking the expectation all the way through, hopefully we can solve for L. Okay. Okay, so I'm going to go back to the big circled thing in orange at the top and take the expectation all the way through. Right here, I just did that one term. So okay, so the expectation of this is equal to the expectation of this. I'm going to write it just so you can see it cancel. This is equal to the expected value of x squared. And then this one, I don't know what that is yet. So plus the expected value of n squared. And the expected value of this is the probability that x is greater than 0. So that is, again, lambda over mu. The expected value of this is -2 times L. The expected value of x is L. And we just wrote down the expected value of the last term, and that is right here. So I get plus 2 lambda over mu, 1 minus lambda over mu, and that's it. So x and x prime, they're just like copies of the same random variable because we're in stationary mode and they're just 2 time points. So they're going to have the same means, the same variances, the same distributions, the same second moment. There is the L I want to solve for. It was somewhere else too. Did I not write it? Oh, yeah, here. A couple L's there. I need this. And then I think we have everything we can solve for L. So the expected value, here's a bullet to kind of separate this out, of n squared. N is the number of customers that arrive during a service time. This is going to be the integral from 0 to infinity. Now I'm thinking about, all right, I was going to save, I was thinking about your question, Sage, but I'm going to save it to the end. So this is the expected value of n squared given the service time is s times the PDF for the service time, which is g of s ds. Okay, if the service time is s, then that means that n, the number of arrivals during the service time, is a Poisson random variable, not a process, but a random variable with parameter lambda times s. And so I need the expected value of that random variable. So recall that the expected value of this Poisson is lambda times s, and the variance of the Poisson is also the same parameter, in this case, lambda times s. And so if I want the expected value of n squared, I usually like to unravel the variance definition. This is the variance of n plus the expected value of n all squared, because usually we write the variance with the difference of those terms. So this is lambda s because the Poisson is so nice, and lambda s squared. So that's what's going into my integral above for that expectation. So I'm going to go back up there. This is the integral from 0 to infinity, lambda s plus lambda s squared. Yeah, and then times g of s ds. I know this is long, but it's like another one of these super fun things where we apply all of our skills all in one place. So don't think about how long this is taking, just enjoy the ride. Okay, the first integral, if I, multiply this out, I've got a lambda, and then I've got the integral of s times g of s, and that is the mean of the service time distribution, which is 1 over mu. And for the second integral, I can pull out this lambda squared, and then I've got an s squared g of s ds, and that is the expected, I still haven't really settled on this, but I guess s is a service time. And that service time can be written, that expectation can, again, using this trick, be written as the variance of s plus the expected value of s all squared. But we were given the variance of s at the beginning of the problem, so, oh, come back. All right, this is sigma squared plus, and our mean was 1 over mu, which is a little confusing. So that is what's going to go in up here. All right, I've got sigma squared plus 1 over mu squared. That all looks good. Maybe I'm going to ask you, I was going to say, can you trust me on this last calculation? But I know I'm not very trustworthy. Where was I? We just found this, and everything else is known except for the L. So I want to solve for L. Trust me? I want to write that L out. So the L is 2 times lambda over mu plus, let me write this neatly, lambda squared, sigma squared, minus lambda over mu squared over 2 times 1 minus lambda over mu. The mean length of an mg1q in equilibrium in stationary mode. Back here, when I canceled these, I assumed I wasn't like canceling an infinity and infinity. So yes, thank you. For this calculation, we need the expected value of x squared to be finite. And what I was just saying before is that we're assuming stationarity, and actually that doesn't mean that the expected value of x is even finite just because you have a stationary distribution. So we need this, and that automatically gives you the lower moment being finite. Let's do a quick check for something we know and love for the MM1Q, because that is an MG1. It's just that the service time distribution is exponential. Okay, in this case, we have exponential service times, exponential with rate lambda. That is not true. That should have been a mu, sorry. And I don't think we need this. We need the variance. So sigma squared is the variance of this guy. And that is for this exponential 1 over mu squared. And so hopefully if I plug this stuff in back up here, let me copy and paste this. Okay, so plugging this stuff in, then here I get a mu squared in the denominator. So these are going to go, and these 2's are going to go. And this is lambda over mu, 1 minus lambda over mu. And if you multiply through by mu on the top and bottom, you get lambda over mu minus lambda. And I don't know if you recall, but that is what we got when we did this by hand using the stationary distribution. The ones that I see used most often, but I don't think it's because they're particularly nice, are gamma service times and uniform service times. But no. Okay, I think I have like a minute and a half or 2 minutes. And I just want to say that the next thing coming up is a simulation break. We're talking about the Metropolis Hastings algorithm. I know that sounds really horrible because in my head, I've got the song. Did you hear the song in one of my videos? I posted in one of the videos, the actual song that's in my head that you're not hearing. We're going to talk about our first continuous state space and the Metropolis Hastings algorithm. So the only thing I think I can fit in right now is just 1 or 2 lines of notation. So this is a thought break here. Suppose that there should be 2 P's in suppose, huh? Suppose that X sub n is a discrete, we're not going to get anywhere, but this is a spoiler, discrete time Markov chain on a continuous state space. We've never talked about this. We got all the way through this course almost without talking about this. Our Pij is now, this is not a limit or anything, is now a P of X comma Y. This has been consistent with my notation for continuous things, not subscripts. And I guess I'm out of time. So one last thing, because I'm not really, I don't know, my clock's right. But the integral of Pxy dy is 1, because this is a probability transition function. So it says that you're currently at some state X, and at the next time point, you should draw the next state from some distribution that maybe depends on X. So what are we going to do with that? We are going to define pi, and then we're going to talk about detailed balance, and then we're going to drag Markov chains into a place where you didn't think they could be. You want to simulate anything that has nothing to do with Markov chains, you might want to use a Markov chain Monte Carlo algorithm. So I can't wait to rub my eyes and read the chat. But yeah, we're done. Thank you.